Now the measurements are made under two different conditions. One is at constant volume, that is QV, that is heat change at constant volume, when all the participating substances are in their standard states. All the participating substances means your reactants and products, all of that must be in standard state. So in this case, it is not a diatomic molecule, right? Carbon is having different 4 bonds with carbon and hydrogen. Hello everyone, this is Ambali Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. Last session, we have discussed about the applications of first law of thermodynamics, and then we studied what is enthalpy as well as heat capacity. Also, we studied an important relationship between Cp and Cv. That is heat capacity at constant pressure and constant volume. That is Cp minus Cv will give you R. That is the universal gas constant. Right. And it is for an ideal gas. So all this we have discussed in the last session. So in today's session, we are going to study about how you can measure the change in internal energy and enthalpy, that is measurement of delta U and delta H, change in internal energy and change in enthalpy. Also, the next topic, that is thermochemistry. So this we will be discussing in today's session. So let us begin with the measurement of delta U and delta H. Okay, so how can you measure the change in enthalpy and change in internal energy? So it is by using an instrument which is called as calorimeter. Okay, so calorimeter will help you to calculate the change in heat, that is whether heat is absorbed or heat is released from the system, right? So if we can calculate the heat absorbed or released, how can we relate it to the change in internal energy or else enthalpy? Let us see. So as I said, we can use this, we can measure the change in internal energy and enthalpy using a calorimeter. So let's see, and this technique is called as calorimetry. Okay, so an experimental technique used to measure energy changes associated with chemical or physical processes is called as calorimetry. So the energy changes which is associated when a physical or chemical change taking place is called as the calorimetry. Okay, and the instrument which is used is called as calorimeter, right? So in calorimetry, the process is carried out in a vessel which is called as calorimeter. So calorimeter is the instrument which is immersed in a known volume of a liquid with known heat capacity of the liquid in which the calorimeter is immersed, and it is possible to determine the heat evolved in the process by measuring the temperature changes. Okay, so we can calculate the change in heat or the heat evolved or heat absorbed in the process, right? And how can we measure it? By using the temperature changes. So the calorimeter will be immersed in a known volume of some liquid, right? And by measuring the heat evolved, right? The amount of heat evolved or absorbed, by measuring the temperature change, we can calculate the heat change, right? Now, the measurements are made under two different conditions. One is at constant volume, that is QV, that is heat change at constant volume. We can measure the heat change at constant volume. That means the volume will not change, the volume will be kept constant, which is equal to what we have already studied. This heat change at constant volume will give you the change in internal energy. Right, okay, and the next one at constant pressure, that is heat change at constant pressure. Even this we have already studied, which will give you the change in enthalpy. Delta U is equal to QV and delta H is equal to QP. So if we can calculate the heat change in constant volume and constant pressure, we can calculate delta U and delta H. So this is how we do the measurement of delta U and delta H using calorimeter. So first let's begin with the measurement of delta U. Okay, so measurement of heat change at constant volume, that is delta U measurement. Okay, so we are going to calculate the heat change at constant volume so that we'll get the change in internal energy. How this is happening, let's see. So for chemical reactions, heat absorbed at constant volume is measured in a bomb calorimeter. Okay, so this is called as bomb calorimeter. You can see it in the figure. So this is what is the bomb calorimeter. Right, now here a steel vessel, which is called as the bomb, is immersed in a water bath. This ensures that no heat is lost to the surroundings. Okay, so as you can see here, this part is called as a steel bomb. Okay, inside which you can see here, the sample will be kept. Okay, and as you can see here, this is the steel bomb and outside it, it is surrounded by water, or else we can say that the steel bomb is immersed in water, right? Okay, and this ensures that no heat is lost to the surroundings. Okay, that means it is completely sealed inside, right? The sample is inside the bomb calorimeter and surrounding the bomb you have the water as well. So there will be a constant volume here. There won't be any change in volume in this condition. Right? Okay. Now, a combustible substance is burnt in pure oxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. So now, as I said, inside this bomb, there will be the sample which is kept and there are ignition wires here. You can see the wires here. Right? Using this, the sample undergoes combustion. Right, and in the presence of pure oxygen, yes, combustion will happen in the presence of oxygen, right? And that is being supplied through this pipe. You can see oxygen supply through this one. Okay, so the oxygen enters here, combustion will start taking place. And what happens? It is an exothermic process, so the heat is evolved. Right, heat is released. So where is this heat getting transferred to? So the heat which is released from this reaction, it is getting transferred into the water. Okay, so by measuring the temperature initially and after the reaction, we can calculate the temperature difference, right? So from that, we can calculate the heat change, right? I hope you understood. Again, inside the bomb calorimeter, we have kept the sample. Using the ignition wires, it undergoes combustion and there is a constant supply of oxygen as well, right? And as it is an exothermic reaction, the heat which is released will be transferred to the water which is surrounding the bomb. Okay, so by measuring the difference between the temperature initially, that is before the reaction, and after the reaction, we can calculate the temperature difference from which we can calculate the heat change. Okay, right. Now, since the bomb calorimeter is sealed, its volume does not change. So, the heat change is happening at constant volume. The energy changes associated with the reactions are measured at constant volume. Okay, so at constant volume means we know that delta V is equal to 0. Okay, so therefore no work is done. We know that the equation is minus P delta V. When delta V is equal to 0, work done will be also equal to 0. The temperature change of the calorimeter produced by the completed reaction is then converted into QV by using this particular reaction. Even this we have studied. Yes, Q is equal to C, that is heat capacity, into M, that is the mass, into delta T. Okay, so this temperature difference we can calculate using this bomb calorimeter, right? And the mass and heat capacity is known. We can calculate the heat change, and this heat change will be at constant volume, which will give you the change in internal energy. So this is how you calculate or measure the change in internal energy. I hope it is clear. So this instrument is called as bomb calorimeter. Now moving on to the measurement of change in enthalpy. So the measurement of heat change at constant pressure can be done in calorimeter. So it is now we are going to conduct at constant pressure. Earlier it was constant volume. Now we are keeping the pressure constant. So we know that delta H is equal to QP. We already know that. So therefore heat absorbed or evolved at constant pressure is called as the heat of the reaction or enthalpy of the reaction. Okay. We can also write it as enthalpy of the reaction, that is delta RH. R stands for reaction, right? So if it is an exothermic reaction, heat is evolved, right? Heat is evolved and the system loses heat to the surroundings. Therefore, QP will have a negative value. Hence, the delta RH, enthalpy of the reaction, will be also negative. So, if it is an exothermic reaction, exothermic means system is losing its energy. That means QP will be negative, right? It is losing its energy. So, it will be negative. Hence, the enthalpy of the reaction will be also negative, right? And if it is an endothermic reaction, endothermic reaction means the system is getting energy, right? So, in that case, QP will be positive, right? Heat is absorbed by the system and hence delta RH, that is enthalpy of the reaction, will be also positive. Right. So, the same way, if you are able to calculate the heat change at constant pressure, we can calculate the enthalpy of the reaction. Okay. And if it is an endothermic reaction, it will be a positive value. And if it is an exothermic reaction, it will be a negative value. So, I hope the measurement of delta U and delta H is clear for you. Right. Now, moving on to the next important part, that is called as thermochemistry. Now, what is thermochemistry? Let's see. It is a branch of chemistry that deals with the heat changes during physical and chemical transformation. Okay. So, it studies about all the heat changes which is associated when a physical or chemical reaction takes place. So, let's see what is a thermochemical equation then. We already know what is a chemical reaction. We have already studied how to balance chemical reactions, all of that. Now, what is the difference between a normal chemical reaction and a thermochemical equation? Okay. So, now let's see what is a thermochemical equation. So, we have already studied what is a chemical equation, how to write a chemical equation, how to write a balanced chemical equation. All these we have already studied from the lower classes. Now, what is the difference between a normal chemical equation and a thermochemical equation? Let's see. So, the thermochemical equations are a balanced chemical equation in which the enthalpy of the reaction during the reaction and the physical state along with the allotropic state of the reaction and products are indicated. Okay, that means, right, okay, it is a balanced chemical equation itself, but the states of the reactants and products will be mentioned as well as the enthalpy change in the reaction associated should be also mentioned. Okay, that is why it is called as a thermochemical equation. Okay, so the physical state of each of the reactants and products needs to be mentioned along with the enthalpy of the reaction. So, as you can see here in this example, carbon and oxygen is combining to form carbon dioxide. So, carbon is in the solid state, which is represented by bracket and in the bracket S. S stands for solid, right? And oxygen, which is in the gaseous state, combines to form carbon dioxide, which is also in the gaseous state. And also the enthalpy change is given as minus 393.5 kilojoule. So, from this minus which is shown here, indicated here, you can also understand that it is an exothermic reaction, right? Okay. So, this is how you have to represent the thermochemical equation. Okay, by mentioning the physical state of the reactants and products as well as the enthalpy change associated. Right. Now, moving on to the next one, the enthalpy change during a reaction is called as the reaction enthalpy. Okay, so the enthalpy change. Okay, the enthalpy change means we have already studied this. Okay, enthalpy change during a reaction is called as reaction enthalpy. So, we mention it as delta RH. Okay, so that is reaction enthalpy. It's also called as reaction enthalpy. The enthalpy change of a chemical reaction is given by the symbol delta RH. And how can we calculate it? It is the sum of enthalpies of the products. Okay, minus the sum of enthalpies of the reactants. So, we know that in a chemical reaction or a thermochemical reaction, there will be reactants and products. So, if we can calculate the sum of the enthalpies of the products and subtract it by the sum of enthalpies of reactants. So, we can write the equation as reaction enthalpy is equal to H of products, that is heat, the sum of all the enthalpy changes. So, that is equal to the sum of enthalpy changes of the products minus sum of enthalpy changes in the reactants. Okay, so I hope that is clear. Now, moving on to standard enthalpy of reaction. So, we know that what is enthalpy of the reaction. Now, what is standard enthalpy of the reaction? So, the standard word stands for when the reactants and products are taken in their standard state. So, let's say the standard enthalpy of the reaction is the enthalpy of the reaction itself when all the participating substances are in their standard states. All the participating substances means your reactants and products, all of that must be in standard state, right? The standard state of a substance at temperature 298 Kelvin is its pure form at pressure 1 bar. So, standard condition means temperature 298 Kelvin, pressure will be 1 bar. And the standard conditions are denoted by adding the superscript to the symbol delta H. So, how you can represent it is, we know this is how you represent the enthalpy of the reaction, right? And if it is in standard condition, you have to put a superscript, that is delta RH naught. Okay, on top of H, you have to put this symbol. Right, delta RH naught, which will indicate that it is in standard conditions. Right, so this is not in standard conditions, but this is in standard conditions. Right, so this is how you have to represent it. So, what is standard enthalpy of the reaction? It is the enthalpy of the reaction itself, but when all the participating substances are taken in their standard state. Okay, now moving on to standard enthalpy of formation. Yes, the next one is standard enthalpy of formation. So, the standard enthalpy change for the formation of 1 mole of a compound from its elements in their most stable states is called as standard enthalpy of formation. Okay, so it is the enthalpy change for the formation of 1 mole of a compound. Okay, 1 mole of a compound from its elements in their stable states. Right, so to form 1 mole of a compound from its corresponding elements, how much energy change, how much enthalpy change is associated, that is called as the enthalpy of formation, and it is represented by delta FH naught. Again, it is in standard condition. So, if it is carbon plus oxygen giving carbon dioxide, right, from its elements, carbon dioxide is the product here. It is formed from the elements, that is carbon and oxygen. Okay, so the enthalpy change which is associated to form 1 mole of carbon dioxide, it is 1 mole, right? It is 1 mole from its elements in their standard states is called as enthalpy of formation, and the delta H is given as this. This is called as a thermochemical equation. Just now we studied it, and it is important to note that a standard molar enthalpy of formation, delta FH naught, is just a special case of delta RH naught, where 1 mole of a compound is formed from its constituent elements. Okay, so I hope it is clear. So this is called as enthalpy of formation. So the next one is standard enthalpy of combustion, delta CH naught, standard enthalpy of combustion. Okay, so again from the name itself we can say that it is under standard conditions, right? So the standard enthalpy of combustion is defined as the change in enthalpy that takes place when 1 mole of a substance is completely burned in air or oxygen at a given temperature. Okay, so it is combustion, that is 1 mole of a compound undergoes complete combustion in presence of oxygen at a given temperature, and it has to happen in standard conditions. So let us take this example, C6H12O6, that is glucose, in presence of oxygen, it releases carbon dioxide and water, and the enthalpy of combustion, that is standard enthalpy of combustion, is given as 12802.0 kilojoule per mole. Okay, so this is called as the enthalpy of combustion. That is the enthalpy change which is associated when 1 mole of a compound undergoes complete combustion in presence of oxygen at a given temperature. Moving on to the next one, that is enthalpy of atomization. Now it is the enthalpy change on breaking 1 mole of bonds completely to obtain atoms in its gaseous phase. The enthalpy change in this process is known as enthalpy of atomization. Okay, I hope it is clear. So that means it is the enthalpy change associated. So that means it is the enthalpy change which is associated when 1 mole of bond is broken down to obtain the atoms in the gaseous phase. It is in the gaseous phase. So for example, H2 gas is broken down into 2 atoms of hydrogen, right? It is a molecule here, H2 molecule. It is broken down into 2 hydrogen atoms in its gaseous phase. So the enthalpy change associated with this particular reaction is called as enthalpy of atomization. So from the name itself we can say atomization, atoms are formed in its gaseous state, right? Now bond enthalpy. Next one is bond enthalpy, which is represented by delta bond H0, again in standard condition. The bond dissociation enthalpy is the change in enthalpy where 1 mole of covalent bonds of gaseous covalent compounds is broken to form products in the gaseous phase. Okay, so it is quite similar with the previous one. It is the enthalpy change associated when 1 mole of covalent bonds of a gaseous compound is broken down into its constituent elements. Now moving on to next one, in diatomic molecules. Okay, in diatomic molecules, consider the following process in which the bonds in 1 mole of hydrogen gas are broken. So, in this case, we are talking about a diatomic molecule. That is, only 2 atoms are present. So, 1 mole of bond is broken in this case, 2 hydrogen atoms are formed. So, the enthalpy of atomization in standard enthalpy of atomization is given as 435 kilojoule per mole. In the case of Cl2 also, right? The enthalpy of atomization means from Cl2 it is getting broken down into 2 atoms of chlorine, and the enthalpy, standard enthalpy of atomization is 242 kilojoule per mole. Next is O2, broken down into 2 atoms of oxygen, and the enthalpy of atomization is 428 kilojoule per mole. So this is in the case when these are diatomic molecules. Diatomic molecules means it will further break down into only 2 atoms. Now, if it is a polyatomic molecule, that means more than 2 atoms are present, then there is a small confusion there. Okay, so next moving on to in polyatomic molecules, that means it is not just 2 atoms, there are more than 2 atoms. In that cases, there is a difference in the condition. So let's see. In methane, so we are going to consider methane, that is CH4. Okay. All the 4 carbon-hydrogen bonds are identical in bond length and energy. However, the energy is required to break the individual carbon-hydrogen bond is different in each step. That means that initially we have CH4. So in this case, it is not a diatomic molecule, right? Carbon is having different 4 bonds with carbon and hydrogen, right? So even though the bond length is the same for each of this carbon-hydrogen bond, still the bond dissociation energy is different. That means that let's assume that this is the first carbon-hydrogen bond which is breaking. So CH4 is breaking down into CH3 and 1 H is broken. Okay, 1 H is released. That means that now what is left here? CH3 and this hydrogen atom is released. Right. So in this case, the bond enthalpy, the standard bond dissociation energy is 427 kilojoule per mole in this case. Now what is left here? It is just CH3. It is just CH3, and in CH3 we are going to break the second bond, that is next carbon hydrogen bond. So from CH3 we are going to break down into CH2 and H. So now the bond dissociation energy will be different, right? So because we are starting from CH3, not CH4. So it will be plus 439 kilojoule per mole. right? And the next one will be from CH2, right? Now already this bond is gone. Now there are only 2 hydrogen bonds. Now out of this, one will be breaking. So what happens? CH2 gets converted or broken down into CH and H. So the bond dissociation energy again will increase. It will be 452 kilojoule per mole. And the last one will be from CH, right? Broken down into carbon and hydrogen. And the bond dissociation energy will be 347 kilojoule per mole. So I hope the point is clear to you, because it is, even though the bond lengths are same, each of the bonds is broken down at a single time. Okay, so this is happening in different steps. That means the bond dissociation energy associated with each of the steps will be different. Therefore, we have to take the average of this, right? Or the mean enthalpy of this. So therefore, the overall reaction can be written as CH4 broken down into carbon and 4 atoms of hydrogen, right? C plus 4 atoms of hydrogen. So totally the enthalpy of atomization will be 1665 kilojoule per mole. Okay, so I hope this is clear, right? So this happens in different steps, and the enthalpy of atomization or the bond dissociation energy will be different in each of the steps. So the total enthalpy will be a sum of all this. Clear? Right. Moving on to the next sum. So in this case, we use the mean bond enthalpy of carbon and hydrogen bond. So for example, we calculated the value for the enthalpy of atomization as, that is from methane, carbon plus 4 atoms of hydrogen, right? And the standard enthalpy of atomization was calculated as 1665 kilojoule per mole, right? This was calculated. But in such cases, we have to use the mean bond enthalpy. So that means that the bond dissociation energy of carbon-hydrogen bond at standard condition will be equal to 1/4 of the enthalpy of atomization. Why? Because there are 4 carbon-hydrogen bonds which are breaking down, right? So that is why this 1/4. So the mean value will be 1/4 of 1665 kilojoule per mole, that is 416 kilojoule per mole. Okay, so it is not 1665 kilojoule per mole, which is the mean enthalpy. It is 1/4 of that, because there are 4 carbon hydrogen bonds which is broken down. So I hope that is also clear. So this mean bond enthalpy of carbon hydrogen bond is calculated if and only if there are polyatomic molecules. That means more than 2. In case of only 2, in the case of hydrogen molecule, oxygen molecule, in this case there will be only 1 bond dissociation enthalpy. Okay, it is easy to calculate. In polyatomic molecules, you have to calculate in this way, that is mean bond enthalpy. In this case, there are 4 carbon hydrogen bonds, that is why 1/4 of the value will be your answer. So I hope that is clear. So in next session, we are going to study about the enthalpy of solution, lattice enthalpy, and enthalpy changes during phase transformation. Okay, so I hope the topics we have covered in this session is clear for you. So that's all for today. Thank you.